All right, so here's the problem. It says a 4.53 gram bullet is traveling at 473 meters per second when it enters a tree, and after it exits the tree, it is moving at 238 meters per second. Where did the lost kinetic energy go? So, what we know about this one is the following. Start off with solution. And what we're going to use here is the first law of thermodynamics in its more general form, which says delta K, which is change in potential kinetic energy, plus delta U, which is change in potential energy, plus delta E internal is equal to Q minus W. In this particular case, I'm going to go on the assumption that basically the bullet was fired horizontally, so it shouldn't really be changing significantly at these high speeds and height. So the potential energy change should really be minor. Uh, Over the whole thing, even though gravity's pulling on it, it's not going to be a big deal. So that's going to be a zero. What we're going to work with, though, is we're also not necessarily assuming that any excess heat was brought in from the environment. So I'm going to assume Q is zero, and I'm going to assume W was zero as well. You probably have already figured out where you think the energy goes. And yes, we had a certain amount of energy, which we'll calculate in a second, as kinetic energy associated with the bullet. But if you were to actually find the shell, which logically will go through, bore a hole through the tree, and then leave the back of the tree and embed in something else or fall to the ground, where in principle you could find it and pick it up. So if you were to do these two things, one, pick up that bullet, you would find that it's very hot. So obviously some energy can go into that. You would find it quite mangled. Obviously some energy went into crushing it. It doesn't necessarily get crushed coming out of the barrel of the gun, that's for sure. So if anything, it gets scraped a little bit. That's about it. But when it hits the anything for that matter, it's going to flatten out and stuff like that. That's going to take away some energy. And if you were to stick your finger in the hole that the tree left, that would be pretty warm too. So it's probably some heat delivered to that as well as various other work. So what I will do is I'll first calculate delta K. So the delta K is supposed to be K final minus K initial. And of course, K we know is 1 half mv squared. We also have 1 half I omega squared for things rotating and stuff like that, but we're just not worried about any of that. We're just thinking about the bullet coming through. So we're going to have a common factor of 1 half m, and the m is 0.00453 kilograms because the mass was actually in grams. And then I'm going to take that and do 473, or excuse me, it's final minus initial. I'm going to do 238 meters per second squared minus 473 meters per second squared. You can see this is going to be uh, a decrease in kinetic energy. And now we can calculate it. And just for the record, even though I factored it out to save time, I still want to know roughly what that kinetic energy is just because I'm a information hound. So we're going to say zero point 0.5 times 0.00453 times 238, and that number is squared. So that gives me 128.3 joules minus, now I'm going to do zero point 0.5 times 0.00453 times 473 squared. And that one's going to give me 506.7 joules. And then when I subtract those two, oops, helps if you type them properly. And I carried a lot of extra digits to do the subtraction. I basically carried all the digits it gave me. And this gave me a figure of 370, negative 378.45. So I felt bad about only adding one extra sig fig on the previous line, so that's why I did subtraction with more of them. And these two are both it's non-significant figures. So that's the change in kinetic energy. Now that change in kinetic energy can be put in the first law of thermodynamics, such that you say negative 378.45 joules plus delta U, which I argued was zero because we're ignoring changes in potential energy, uh, plus, in this case, the internal energy of the bullet. Since our system seems to be the bullet, the internal energy is definitely going to increase. And like I said, other stuff, we're going to maul it all to pieces and that sort of thing. So basically, all we have left is delta E internal on the left-hand side, and that's all equal to zero. So it turns out that delta E internal would actually be equal to that change, the negative of that change in kinetic energy. So it's going to be a positive 378.45 joules. But that's, that's a broad uh, stroke that we just made, saying all of this is going in internal energy, and it is. But I want to remind you that other than ideal gases, the internal energy can, in principle, depend on things other than temperature. What we find is, and you'll read about this in the free expansion section of this chapter, what we find is that gases actually matter just a little bit. Their internal energy matters a little bit on things like pressure and volume, not just temperature. And the way we've done that is basically if you treat an ideal gas, whether it be a monatomic, diatomic, polyatomic ideal gas, a change in temperature is the only thing that causes a change in internal energy. But when we actually allow a real gas to do a free expansion, we find that the temperature goes down a little bit. So what we do know is the internal energy definitely changed, even though we didn't do any of the other stuff that's normal. So we think that that means that the that the gases that aren't ideal do depend on volume and pressure as well as temperature. So, anyways, that's just a short synopsis of what they're telling you in the uh, I think they call it the free expansions subsection. Actually, let me just check real quick. I'll pull the book up. I have it right here. It might even have been a subsection, come to think of it. Yep, that's what it was. It was a subsection of 1907. So, anyways, we'll go on now. We've finished the intro section to the ideal gas law. I mean, to the first law of thermodynamics, and yeah, free expansion is the last section of the section on thermodynamic processes in the first law. So, anyways, at the end of that, you'd learn that. Now that I've gotten this done, I wanted to point out a little bit of what was discussed within the thermodynamic processes section. I mentioned to you how I wouldn't be doing all the derivations. Again, all those derivations you can find in your book. You can also find them on my YouTube channel. If you want to look for me doing the lectures on chapter 18, you'll find the derivations in there. But again, I don't see that it's critical for that. That is definitely a holy grail if you're interested in trying to maybe major in physics, or if you're wanting to major in engineering. Doing that would make you leaps and bounds above a lot of your fellow engineering students when you get to the next level. So only focus on doing those derivations if you can. But if you can't, it doesn't mean you're not capable. It doesn't mean you're not smart enough to be an engineer or a physicist. It just means that you right now are not yet ready to do it. So let me point out that the processes we mention here are processes that we have for a system. We normally call them like thermodynamic processes, one of which is isothermal. And you can see isothermal means a process in which the temperature doesn't change. So with that in mind, that means delta T is equal to zero. And remember, if we're thinking about ideal gases, internal energy depends only on the temperature change. So if there's no temperature change, then the internal energy can't change. Therefore, our first law of thermodynamics, ignoring the mechanical part, is delta E internal is equal to Q minus W. But we just found for isothermal ideal gas like uh, isothermal processes of an ideal gas will result in delta E internal being zero. So Q is just equal to W, meaning whatever heat you add to the system will go directly into work. So by causing, like, if the system is a gas inside of a cylinder with a piston sitting on top of it, it'll actually cause the putting heat in will actually cause the piston to lift up a little bit. Okay. Also, if you're using delta T equals zero, then you know that T should be a constant. And the ideal gas law, which is PV equals nRT, has the N and the R and the T all being constants. So you can take the formula for work, which is the integral of PdV, as I've shown you here, and solve that P in the ideal gas law. Remember, the ideal gas law was PV equals nRT. So P is equal to nRT over V. And now if you plug that in for P, the nRT can come out in front of the integral because the T is a constant, and you get the integral of dV over V, which is a natural log, and therefore the work in that scenario is just nRT times the ln of the final volume divided by the initial volume. Does that make sense? You see how that follows
Yeah,
the
go to
delivery?
well, explain the how we landed at the the natural log of the final volume over the
Okay, this right here.
yeah. So yeah, the
The,
integral of 1 over V is the natural log of V, right?
right. And then you do the natural log of V final minus the natural log of V initial, and the difference of logs is equal to the
Is
log of the
oh, that's
divisor.
yeah, it's a quotient.
Yep. So that's it. Yep. Good job. Another process is adiabatic, and that's one that can be done usually by, like, when we did the calorimeter experiments or the calorimeter calculations, we were making the assumption that we built something insulated well enough that heat can't be transferred into the system or out of the system. But it also turns out that adiabatic can happen because adiabatic means no heat flowing. Heat flowing is actually a fairly slow process. You've got to wait for molecules to bump into other molecules, and that's not good enough. You've now sped up the molecules, but they're not sped up in a random way. You have to wait for that speeding up to distribute itself so that all of them have a new net average kinetic energy, and that takes time. So sometimes adiabatic can be accomplished just by a rapid technique. For instance, we often, when we're working with heat engines, which is basically car engines, if you're in the field of engineering trying to design a car engine, we often make the calculation assumption that the piston or the gas in the piston exploding is an adiabatic process, specifically in that heat can come in, but once it explodes, there's a rapid adiabatic expansion. So whatever that temperature was right after the explosion, it stays that temperature because it just hasn't had, or it not stays that temperature, sorry. Whatever heat was created is not actually processed by going outside of the system. And that's
Well,
because it just takes too long.
wouldn't it at the beginning phases reach equilibrium with the if the metal around it is at a cooler temperature?
Yes, yeah, and like when you first crank up an engine, obviously you're slowly getting that engine going from outside air
Right.
temperature
Because
to
that
how hot
explosion
you know a car is.
process, because that explosion process within the cylinder is obviously at a higher temperature, and then obviously therefore the temperature of the whole block
Right.
will increase over time, and then eventually it would all reach equilibrium to an extent.
Yeah, yeah, it'll reach some high temperature that it'll stay for a long period of time, and it's probably a fairly characteristic temperature that depends only on the temperature. Well, it depends on the driving conditions, whether you're nailing it or just
Right.
driving at 60 miles
Right.
per hour for say 6 hours straight. But
And
it
then
also
also probably
depends
the
on the air
specific heat
temperature.
capacity of the metal.
Yeah, what metal they use, a aluminum
Yeah.
block versus a steel block and that sort of thing. So, yeah, but the main part is, yes, the individual piston, you know, doing the force expansion just during that small time interval, no heat is going to be delivered. But yes, now the piston's a little hotter. Now the piston chamber's a little warmer. And eventually, even that small amount of heat that might have got through adds up to get the whole engine as hot as what we're talking about. So,
Okay. But just to review, the adiabatic process is where the heat is trapped inside the system.
yeah, you can think of it as that way. Remember, systems don't own or have heat. The heat is just the energy in transfer.
Well, yeah, it's
So,
a
yeah.
transfer of energy, but the hmm, I guess the energy is therefore
Restricted inside. I,
right. Okay.
yeah,
All right.
yeah.
Yes.
It's the same thing. It's just you wouldn't want to use the word heat to say it's trapped, because it's only becomes heat as opposed to energy when it's in the process of transferring from one object to another. Just a
And is
little
this always in the
pedantic
case of
thing.
temperature
Uh, uh, what
with
do you mean?
adiabatic?
Oh yeah, adiabatic. The temperature can definitely change, but adiabatic means there's no heat flow into the system or out of the system. That's the strict definition of adiabatic.
Okay. All
That
right.
makes sense. So yeah, the ramifications of temperature can vary depending on what kind of system you're dealing with. But the main thing is the Q in the first law of thermodynamics is going to be zero. That's why I wrote Q equals zero, and then I showed that that meant the second law. I mean, the first law of thermodynamics says delta E internal is equal to Q minus W, but now Q is zero, so it's just delta E internal equals negative W. I'm also giving you here in purple a result that your book derives in this section. In fact, it's a pretty straightforward derivation. It's kind of nice, but basically, when you have the added condition that the process is adiabatic and an ideal gas, then you can show that the pressure times volume to the gamma power is a constant. So what we did before, for instance, with ideal gas, you don't always have to use it as PV equals nRT. You can also use it as P times V, P1 V1 is equal to P2 V2, as long as the temperature doesn't vary and as long as it's a closed container so that no increase or decrease of the number of moles happen. You could also use P1 V1 over T1 equals P2 V2 over T2. And in that case, the only thing that has to be true is that it's an ideal gas, which acts just like a real gas, but also that the number of moles or the mass of the gas, either one can't change. But you could also use, instead of just PV, like I did, or PV over T, you can also use P over T. So P1 over T1 equals P2 over T2, or V1 over T1 equals V2 over T2. All of those are different things we can use with the ideal gas law. But obviously, when we do that, all the other variables from the ideal gas has to be a constant if we're treating it that way. So like if we're using P, V, and T, so we say P1 V1 over T1 equals P2 V2 over T2, that the only variable that's left out there is the N from the ideal gas law. So that just means it's a fixed amount of gas, a fixed number of moles of gas. If we're using P1 V1 equals P2 V2, then we also have to add that the temperature is a constant. If we're using P over T equals P over T, then it's the N has to be constant and the volume has to be constant. Y'all get what I'm saying there? Okay. All right. So the next process, and by the way, the gamma is the specific molar heat, CP at constant pressure, divided by the specific molar heat at constant volume. That's why they're subscripted P and subscripted V. We're going to use this in some of the examples in a second. So that's why I wanted to make sure you knew what those were. Even though I'm not showing you derivations, we are going to make use of that stuff. Uh, Another process is isobaric, which you might remember. The bar is a unit of pressure, an old unit of pressure that used to be used. So that's what they're saying. They're saying it's constant pressure. Iso just means equal or constant. So in this case, isobaric means the pressure is a constant. And then the work, which is the integral of PdV, becomes just P times delta V. So you can also alter the first law of thermodynamics to say delta E internal is equal to Q minus P delta V. So that's how the first law of thermodynamics is affected in the isobaric process. Does that make sense? Okay, and then one more, and I'm happy to report that yeah, they're converting slowly to just using the phrase isovolumetric. Even though it's a nastier, bigger word, isochoric is what we've used traditionally for it, but that's not easily seen to be volume, so you always forget. So I'll just tell you isochoric and isovolumetric are the same thing. They mean constant volume. And if the volume's constant, since work is supposed to be the integral of PdV, there can be no change in V, so the dV is essentially zero, which means there's no work done. And in that case, delta E internal equals Q minus W becomes delta E internal is just equal to Q. Okay, so those are the ramifications of those various processes. What you'll probably learn a lot from this, especially if you try to focus on the derivations that they do for CP and CV, like one of the things we learn is CP minus CV is equal to R. That's another derivation that your book does. It's a nice derivation. It's easy. And it also shows you what thermodynamics is about. So if you guys are going on for engineering, you're going to take engineering thermo, and the crux of thermo is just a ton of derivatives. You're just taking derivatives over and over and over and over again. And then occasionally you'll use those derivative or differentials to integrate in terms of like an idea, in terms of like a differential equation. And from that, you can get equations like PV to the gamma equals a constant. Okay. But yeah, CP minus CV turns out to be R. And then we also turn out, I think that CP turns out to be, I want to say 5/2 R. Yeah, that's it. 5/2 R. And then therefore CV turns out to be 3/2 R. So 5/2 minus 3/2 equals 2/2, which is one. Yeah. So those are some results that we find as well, and I'm going to make use of those, and I'll show you the tables about why we're using them. I want to express to you that this CP that I'm using and this CV that I'm using, they have very specific units, which are joules per mole Kelvin, are calories per mole Kelvin. Okay. Same thing with CV. That's joules per mole Kelvin again. And I should point out that the CP is just basically the molecular weight of the substance times CP that we used before, where this CP has units of joules per kilogram Celsius degree. Okay, so that's how you actually calculate the capital CP that we're using for the ideal gases. And the capital CV is done the same way as well. You would take the specific heat at constant volume and multiply it by the molecular weight of the substance that you're talking about. For instance, water vapor. You look up the specific heat of water vapor at constant volume, and you just multiply it by the 18.0 grams per mole, and that'll actually convert it to joules per kilogram, or joules per mole, or calories per mole instead of joules per kilogram or whatever. Does that make sense? Your book explains all this too, but like I said, this is something that's coming up. Now, what you might want to look at, and this is the part where the learning comes in, so I want to definitely express that. Can either of you think of a reason why CP minus CV gives a positive value, or more directly, why do you think specific heat at constant pressure would be larger than specific heat at constant volume? It's perfectly normal for students not to be able to answer this. So don't feel bad
Wait,
if you
say that
don't get it.
again.
Why does CP, the specific heat at constant pressure, why is that larger than CV, the specific heat at constant volume? So it's perfectly normal, like I said, to not necessarily know this, but think about it this way. Specific heat is supposed to be a measure of how much heat it takes to change the temperature of something. Okay, so that's how much Q is required to, say, change a mole, in this case, since we're talking about the molar specific heat, to change a mole of a gas from 14 degrees Celsius to 15 degrees Celsius. If you're doing it with constant pressure, uh, that is going to be bigger. But if you're doing it with constant volume, if you look at the first law of thermodynamics, you see that if it's constant pressure, well, again, if you see that it's constant volume, then you know the work is going to be zero. So every bit of the heat that goes into changing the internal energy, and for an ideal gas, that means changing the temperature. Whereas if it's constant pressure, some of that energy can go into work, and then the rest goes into changing the temperature. And you can see that from the first law of thermodynamics. Does that make sense? Y'all see how that delta E internal, which for ideal gases is only dependent on T? Y'all see that how that makes that true?
Yeah, on that last bit you said delta T, what did you just say? You said delta T what?
Okay, yeah. So delta E internal, if at least if you're dealing with ideal gases, and real gases behave like ideal gases in most situations, but if you're dealing with ideal gases, then delta E internal is really only, I'll write it right here so you'll know the formula. Delta E internal is equal to some number of degrees of freedom over 2 times K, oh, excuse me, times N, the total number of atoms, times K times T. Excuse me, and it shouldn't be times T. Your book made the same mistake, so watch out. There's one like that. It's got to be delta T in that case. So you see that the first law of thermodynamics, which is written many times here, like there, for instance, we're talking about heat going in here. If it's at constant pressure, then some of this heat can go to W and some can go to changing the temperature. But if it's constant volume, then this is zero, so it all has to go to changing the internal energy and therefore changing the temperature. Does that make sense?
Right.
So
Okay.
we should expect a priori that CP is bigger than CV.
Right.
Okay. All right. That's the main thing that I wanted to make sure y'all get out of that, because that's sort of a fundamental idea. That's something that we've learned about substances, and it makes good sense. So it's a nice story that you can hold on to remember the fact. So now that I've gone over that, let's go over another example. This says, in this figure, or in the figure, we see a PV diagram expanding isothermally. Notice they said expanding, so that means the volume is increasing. That's why we see it going from A to the right, and that vertical axis is P pressure, but the horizontal axis is V volume. So going from A to B or from A to C is an increase in volume. So it says, in the figure, we see a PV diagram expanding isothermally and adiabatically, the top line being isothermal, the bottom line being adiabatically. If the initial volumes were both VA and the final volumes VB and VC are equal, as the diagram shows, in which process was more work done? So, do y'all have an idea on that? Can y'all have you have any idea just from what you know about work? For instance, I gave you one of the things that we use to calculate work, which is that equation. That might be enough for you to understand which one of these processes would take more work.
Yeah,
Anybody?
obviously as V increases, the isothermal is going to have a higher pressure.
Uh-huh. So that would make the work more or less.
It's isothermal. Um, I'm going to say more because I'm assuming it takes work to
Remember the other thing. Remember, derivatives give us what about graphs?
the slope,
What do integrals give us?
the area underneath the curve. So
So,
the area underneath the curve for isothermal is larger.
yep, that's it. I figured y'all get it once you register to you. Oh, that's an integral. Yeah, that's area under the curve, right?
Right.
And in fact, that's a big process. So, for instance, when we start doing heat engines, they'll have closed loops like that, and when you
Hmm.
have that, the work done is the area inside of
Hmm.
it because it's plus
Yeah.
the one way and then the bottom's minused out. So in this case, it's just the area under. So yes, that is exactly the result. The answer is more work in the isothermal process. The isothermal, whoa, no, and the ways you can explain that is sort of like what you said. The pressure's higher at every point on the isothermal. Therefore, the average pressure over that change in volume is going to be larger. Therefore, the average pressure times the change in volume, which is a measure of the work, is clearly going to be greater than the average pressure times the change in volume for the adiabatic. So you can do it that way, or you could, in principle, go ahead and calculate the integral. But yeah, that's it. The isothermal uh, expansion takes more work because work equals integral P dV is the area under the PV diagram. So that's one way you can do it. But like I said, you could also just compute it from a idea of the average pressure being larger in the isothermal than the average pressure in the adiabatic, and therefore a larger pressure times the same change in volume should give you a larger work. Does that make sense? All right. So this one says in a car engine, 0.300 moles of a monatomic ideal gas is in a cylinder slash piston chamber and it expands rapidly and therefore adiabatically against the piston. During that process, the gas drops from 1210 Kelvin to 453 Kelvin. How much work does the gas do? So that's what we're shooting for on this one. Anybody have any questions on what that means so far? Okay. Well, we're going to go ahead and start doing it. So, what we're looking at here is a car engine, and it obviously has, let's start with a solution here. I'm going to write solution, and the information we have is that N is equal to 0.300 moles. And of course, that has three sig figs. That's why I wrote it as 0.300. It's monatomic and ideal. And since that's monatomic and ideal, we also know that delta E internal is equal to 3 halves in RT. Okay. You could also write it as in KT, but I'm using 3 halves in RT. So that's another thing we know. We know the initial temperature is 1,210 Kelvin, and luckily they gave it to us in Kelvin, so we know that we don't have to convert it to Kelvin, but because anytime you use the ideal gas law, it has to be in Kelvin, and we know that the
I
final
mean,
temperature.
converting Kelvin and Celsius is like the easiest thing. So
Yeah, yeah, it is. It does. Yeah, that is one of the easiest ones.
just 273.15.
Yep. So we're looking at final temperature 453 Kelvin, and what they want to know is how much work is done. We also know that delta E internal from the first law of thermodynamics is Q minus W, but this was an adiabatic process, so Q
Yeah,
is
Q
equal
should
to
be
zero.
zero.
Yep. So what we see is delta E internal is really going to be done equal to the negative of the work done. So since it's an ideal monatomic gas, we can easily calculate the change in internal energy and then just set that equal to negative W, and that'll give us what W is, which is what they're asking for. So delta E, I probably should write with a pen instead of a laser pointer. So delta E internal is equal to, now this is an ideal monatomic gas, so that's why it's three halves. Remember a second ago I wrote F over 2. Here I wrote F over 2. That degree of freedom stuff I've been hitting at, and I'm going to talk about it a little bit later, so that'll make more sense. But right now, just know that a monatomic ideal gas is single atoms, and them rotating about an axis is really insignificant because the radius of atoms are so small. So really, all we care about is their translational motion left and right, so that's in the x direction, that's 1 degree of freedom. Forward, backwards, that's 1 degree of freedom. And up and down, that's another degree of freedom. So we got 3 degrees of freedom, and that's why it's 3 halves nRT. So,
Oh, okay. But it doesn't matter the radius.
yeah, it's the
I
rotation
mean,
of
that's
it.
determined by temperature.
Right. Yep. The
Okay, but
other
that,
energies it would have would be more likely when you have two atoms bonded together, then they have that large distance of an atomic bond, and therefore the mass is extended out way past 10 to the negative 11th meters. So in principle, it
but the
works a little
degrees
more.
of freedom are just the axes.
What I like to think of it is think of every type of squared variable you have with energy. So like when we did conservation of energy last semester, we had kinetic energy, which was 1/2 mv squared. And that of course is for all translational motion, and each dimension of that is 1 degree of freedom. So you've got v squared for the x dimension, you got v squared for the y dimension, you got v squared for the z dimension. That's 3 degrees of freedom. You also have, for instance, in a diatomic gas, you have that dumbbell that's like this, so it can rotate that
Oh,
way
right.
or this way, but the other one is like around the atom, so we don't count that.
Oh, yeah.
So
Okay.
diatomic would have 5 degrees of freedom, it seems like. But remember, we also did 1/2 kx squared. And it turns out that every time you're thinking about the energy of an atom vibrating next to another atom because it's attached to a spring, that's another degree of freedom, as well as the kinetic energy of the atom moving in that. So that brings in 2 more degrees of freedom. So, yeah, we'll talk about that a little bit more, but that's why we're going with that. Okay.
Okay.
All right. So we're going to say 3 halves nRT. Oop, again, I switched to my laser pointer. And delta T. And that is 3 halves times 0.300 moles times 8.314 joules per mole Kelvin times delta T, which will be final is 453 minus 1210 Kelvin, like that. And now we can compute that. We're going to say 1.5 times zero point 0.3 times 8.314 times parenthesis 453 minus 1210 obviously we can only count 3 sig figs here. So this becomes negative 2,832.2 joules. Only counting 3 sig figs means those two are not sig figs. And now we use the first law of thermodynamics, delta E internal is equal to Q, which we said was 0, minus W. Therefore, W is equal to negative delta E internal, which is positive 2,832.2 joules. Any questions on that one?
Hold on.
Go ahead.
Just real quick, the pressure, I'm just trying to figure out why the temperature would drop.
Ah, so determine the internal energy change when 1 liter of, oh, excuse me, I'm reading the wrong one. In the car engine, zero point 0.3 moles of a monatomic ideal gas in a cylinder piston chamber expands. Uh, Expansion
Oh,
causes
sorry.
cooling.
I meant, well, I was just kind of following what you're doing too in the book.
Hmm.
They have one where the temperature would drop. So like, because I mean, it's kind of a similar scenario where in an engine.
Hmm.
So in the other direction, so the gas cylinder expands rapidly and adiabatically against a piston. In the process, the temperature of the gas would drop. The gas drops from a higher temperature to a lower temperature. Why?
Yeah.
I'm just trying to think of like that situation. But
Well, remember expansion. We normally think of, cells of air. If you're talking about meteorology, we think of cells of air when they actually go up, they expand, and when they expand because it's lower pressure, and that lower pressure
oh,
causing them to expand also tends to make the air cool down. That's why the mountains are a little colder on top, in addition to other things. But yeah, that's one way of thinking about it. That help?
well, does the pressure change in this
Uh,
system?
With this one, we made no claims about it. We don't know anything about the temperature change, or excuse me, about the pressure change. So yeah, I'm not sure in this process.
Okay. I was just
Uh,
curious. I was trying to think of like you would think it'd be the other way around. You know what I mean?
right. Yeah, yeah, I get that, but I'm just sort of glued to the idea that usually expansion results in a decrease in temperature, but I totally get what you're saying. If you're thinking about an engine, normally the expansion is due to a big explosion. But remember, a four-stroke engine, the second cycle is an expansion that basically pulls in new
Oh,
stuff.
right. Okay. All right.
So maybe that's what's tripping you a little bit. Does that make sense? You good on
Yes,
that,
it does.
Jen?
Thank you.
No problem. All right, now example 4, it says determine the internal energy change of 1 liter of water at 100.0 degrees Celsius. I wanted to make sure all three of those sig figs were, or all three of those digits were sig figs, so that's why I did that. When it is boiled completely to form 1,693 liters of gas at one at 100.0 degrees Celsius again. So that's what we're attempting to do. Uh, with this one, what we know is happening here is we're actually changing the state of matter. It's going from water, which is a liquid, by the way, it's going from water to gas. Okay. So what we can do is figure out how much work is done and then figure out how much heat has to be added. And between the two of those, we can then use the first law of thermodynamics to figure out what the change in internal energy is. So what they're asking specifically is determine the internal energy change. So that's what we're looking for. Does that sound like a good process to go through trying to find that change in internal energy?
Yeah, that makes much more sense.
Okay. So what we know
I can
is
visualize this.
there you go. Ooh, we know Q is going to be equal to M times L because that's what you use for the change in state. The temperature's not changing at all. That's why I'm not using Q equals MC delta T. We also have that delta E internal, which is the first law of thermodynamics and therefore always true, is equal to Q minus W. And we also know that work is equal to the integral of P dV. In this case, they tell us that this takes place at 1.000 atmosphere of pressure. So this is at constant pressure, which means it's even better than that. It's just P times delta V. So I will also mention that the latent heat of vaporization of water, the L that we need here, is given by L. This is heat of vaporization of water. That's going to be equal to 22 point, was it 5 or 6? Yeah, 22.6 times 10 to the fifth, and that's joules per kilogram. Yep, checking my units. Yeah, that all works. Okay, so we'll first calculate the Q is equal to ml. And in this case, it's 1 liter of water, and we know 1 liter of water is 1 kilogram. So it's going to be 1.00 kilogram. Keep that in mind, by the way. We have this wonderful idea of water density being 1 kilogram per cubic, or excuse me, 1 gram per cubic centimeter, which also happens to be 1 gram per milliliter, which also happens to be 1 kilogram per liter, which also happens to be 1,000 kilograms per cubic meter. All of that tells you that the liter is dead center between 1/1000th of a cubic meter and 1,000 cubic centimeters. So, in case you ever run into difficulties with trying to convert from liters, it's literally dead in between the milliliter and the millicubic meter. It is the millicubic meter if such a thing existed.
That's one more reason why we should just switch to liters.
Exactly. Yep, yep, yep.
Like like our system, like a pound isn't a pound of water isn't equivalent to a gallon or like a pint or like a unit of measure.
Exactly. It's not, none of that stuff holds anymore. Why are we still using it, right?
Right.
Now, in this case, you actually have to add the heat to the water to make it turn into steam. So the Q is definitely positive. Remember this thinking about latent heat, whether it be fusion or vaporization or sublimation, being positive or negative. That's the whole reason that I do my calorimetry as Q lost equals Q gained. So I don't have to think about those signs. This is an instance where, yeah, you got to think of the sign, and yeah, you got to put more energy in to a liquid to make it a gas. You got to put more energy into a solid to make it a liquid. So we've got that part. Now we can do work. Work is equal to P delta V, which for P, it's 1 atmosphere. And 1 atmosphere is 1.013 times 10 to the fifth Pascal. So 1.013 times 10 to the fifth Pascal per ATM per atmosphere. And then we're doing a volume change of 1,693. Now, in this case, that's actually liters. So I need to divide it by 1,000 to make it cubic meters. So that's 1.693 cubic meters minus 1.00 times 10 to the negative third cubic meters. So again, that's where I was trying to get you to realize that a liter is 1,000 cubic centimeters and also 1,000 milliliters, obviously, but it also is 1/1000th of a cubic meter. So we can just move that decimal 3 places to the left to make it into cubic meters. And this result gives me 1.013 times 10 to the fifth times parentheses 1.693 minus 1 times 10 to the negative 3, close parentheses, and that gives me 17,000. And it did expand, so it was positive work. So that's 171,399.6 joules. Now that only had four sig figs, three sig figs at most. So I'm going to say all these digits are not good. But now we can calculate the change in internal energy. If I quit switching my pencil, delta E internal is equal to Q minus W. So this is going to be 22.6 times 10 to the fifth joules minus 171.3 0.40, say that'll be enough. 0.40, and that will be times 10 to the third, which actually I was kind of stupid. I could have made it 1.71 times 10 to the fifth, and then I'm just realized I'm just adding 22.6 plus 1.71, and that gives me 22, or excuse me, 24.314 times 10 to the fifth joules, where these two are not significant figures. So, does that make sense to everyone?
Is it 10 to the fifth or 10 to the second?
This one was 10 to the third because I put the decimal after 171. The
I
other one
see.
was 10 to the fifth, and the answer is 10 to the fifth. Oops.
Okay.
And I'm trying to make it clearer for you and bigger. Yeah, that one's 10 to the fifth. All right. Any questiones? Working on my
Wait,
Spanish.
so we're adding or subtracting?
We actually, whoa, Nelly, hold on.
Yeah, I
I,
was
I
like,
was
why
thinking I
is
got a
that number
negative.
higher than our initial?
Yeah, nice
Why is our
catch.
final number higher than our initial?
I was remembering the problem I did earlier, which it has nothing, no bearing to
No,
this
you're
one,
good.
and I
Oh,
had a
you said
negative
it
work, and I just
too.
thought it was a negative. But yeah, you're right. Thank you for that. But
And
now I
then
can
with
write
the
it better.
final, you're good.
What's that, Jen?
No, I'm just talking out loud math in my head.
Gotcha. I understand. So I will now correct this, and I'm going to write it as 1.7139 times 10 to the fifth joules. And again, pointing out that. So let me do this right. It'll be 22.6 minus, which is obviously an important point. Thanks for that, Josh. 7139. So that's 20.89 times 10 to the fifth joules. And that is a much more right answer. Sorry about that. I don't even know. Like I said, I think I was thinking that the work was negative, and that wasn't even the last problem where the work was. Oh yeah, maybe that's what it was. No, the work was positive last time too. Oh well,
Wait,
I
hold
don't.
on. 2.6. Oh, sorry. Never mind. I'm just punching this in the calculator.
Yeah, yeah. Uh, I hate how often I make mistakes with my fingers and pushing in the calculator. So it's really
No,
terrible
you're
because I
good.
don't like my arithmetic skills. I'm always making careless mistakes with adding and subtracting. So, anyways, let us move on. Any questions on that before I do so?
Nope.
Okay, so that finishes off the section on processes, and then we go into the molar specific heat. So I wanted to show you a particular thing. This table right here comes from your book. It's table 19.4, and this is of course Giancoli's fifth edition. So just to give it credit, this is almost certainly a violation of copyright, but I don't. I think I might be protected under educational use. But anyways, what we have here is specific heat. If you look at these numbers over here, These are the specific heat units we're used to using, like kilocalories per kilogram Kelvin. A lot of K's in that word. But notice there's no rhyme or reason to them. They look, I mean, nothing, I don't see any patterns emerging. N2 and O2 are both diatomic, yet they have starkly different values. He and Ne are both monatomic, and they have starkly different values, both for Cp and Cv. But if you just make the change to calories per mole Kelvin, look what you get. Very close to 3 for two monatomic gases, very close to 7 for two diatomic gases, very close with a little bit of problems of two triatomic things. And notice the CPs and the CVs, they can be a little different, but not horrible. So we're trying to look for some way to make sense of this. Uh, and it seems like the best bet to make sense is to use these units instead. So when we use these units, calories per mole Kelvin, then we get these nice values. Remember also that R is 8.314, but if you use it in calories per mole Kelvin, you end up getting 1.98. So 1.99, this is very close to just R, which obviously Cp minus Cv, I just told you, was R, so you do expect that. It turns out, though, if you go to a diatomic gas, it's still very close to R. If you go to a triatomic gas, it's still very close to R. And even if you go to a polyatomic, it's still close to R. And Cp over Cv, that was that gamma I told you about earlier. You can see that's 1.67, 1.40, 1.30. So still there's some rhyme or reason with it. Okay. So that's one of the things we learned about molar specific heats. And I gave you the equations, of course, of how to convert them. They were right down here in the purple. So you can convert them by multiplying by the molecular weight of the substance. And instead of using MC delta T, now we're using N, the number of moles, times C delta T, whether it be C sub P or C sub V. Okay. So that's the main part I was wanting to shoot for there. Now that we've got that covered, I can go ahead and start working examples to make some sense of it. But in addition to that, I need to talk about the equipartition theorem and stuff of that sort. So there's this other really good graph. This is a graph of a diatomic gas. Okay. On the vertical axis is the specific heat at constant volume in joules, or excuse me, in calories per mole Kelvin. On the horizontal axis is a logarithmic scale for temperature. Okay. Now, we've been using 3 halves kT as being equal to 1/2 mv squared average, right? Y'all remember that's what we did in the very beginning of chapter 18? We made that derivation. Well, it turns out that's right, but here's the neat thing. We get 3 halves R here because the 3 is supposed to be like a degrees of freedom, but we know there's more degrees of freedom in a diatomic gas than there is in a monatomic. In monatomic, you just have 3 degrees of freedom because it's a ball that's infinitesimal, and therefore the only relevant energies are the 1/2 mv squared in the x dimension, the 1/2 mv squared in the y, and then 1/2 mv squared in the z. But check this out. When we go to diatomic, you should have 5 from what I told you, but I left out another 2 that I sort of hinted at a little bit earlier. So what you see is when you get around, let's say, 70 Kelvin roughly. Again, this is a logarithmic scale, so it's hard to tell. But until you get to about 70 Kelvin, you're only getting 3 halves R as the specific heat. So it seems like at low temperatures, it's really hard to get the atoms that are on the ends of a bond to rotate about that axis or that axis. That's where the other 2 would come from. But once you get solidly to around 180 Kelvin, then you can see that I'm getting access to those 2 additional degrees of freedom. But if you go further still and get closer to 800 Kelvin. Then all of a sudden, it's going to kick up to 7/2. So an additional 2 degrees of freedom. So as I was telling you, the CP or the CV in this case, this is all going just to temperature. Remember, because CV means no work can be done. So all the Q is going straight to changing the temperature. For that reason, we see that the temperature is affected only by the 3/2 because that's what we derived earlier. But the other degrees of freedoms, which gave us 7 total, uh, so obviously there's 4 more. We have this diatomic gas rotating about this axis right here. Okay. That's why these circles are sort of not really circles. They're looking like this because they're saying it's rotating like that. Okay. This one, on the other hand, is rotating about this axis, which is coming out of the page. So this should make a perfect circle instead of a ellipse because it was at an angle. So that's where the fourth and fifth degree of freedom comes from, is those molecules or atoms on the end of that bond being able to rotate about those two axes. It can't rotate about this axis, though. It can in principle, but we find that that doesn't take an appreciable amount of energy, so it evidently doesn't show up at all. But additionally, once you get to that 800 temperature range, it jumps up to 7/2 R. The other two come from 1/2 kx squared. Remember, I said variables squared for energy. So 1/2 kx squared is the potential for a mass on a spring. So these things do have the ability to oscillate back and forth, and that gives it a potential energy 1/2 kx squared. So that's one of those degrees of freedom. But it also gives a velocity 1/2 mv squared that happens to be along that bond, and that gives us another degree of freedom. So that's what that 7/2 that we're talking about up here came from, is from the bonding energy 1/2 kx squared as well as the kinetic energy 1/2 mv squared. Any questions on that? All right, so that's the big part that we're getting out of here. Now, that led us to the idea of the equipetition theorem. And what it says is basically when energy comes into a system, it divides itself statistically perfectly. So if there's 12 degrees of freedom and you put in 12 million joules, each degree of freedom is going to get exactly 1 million joules because there's 12, and that would give each of them the exact same. And that's actually why, like I said, water is a good insulator, because water has many degrees of freedom. It's a polyatomic ion or a polyatomic atom, and it has many degrees of freedom. And only 3 of them, remember the 3 translational, are related to temperature. So if you have, for instance, 9 degrees of freedom, 6 of them, and therefore 2/3 of the energy goes into changing, not changing the temperature, just doing other stuff, and only 1/3 goes into changing the energy. So that's what the equipetition theorem allowed us to realize, is that each mode or each degree of freedom gets exactly the same amount of energy. That energy is 1/2 kT. So 1/2 kT for 1 degree of freedom, 1/2 kT for another, 1/2 kT for another, so on and so forth. So that allows us to do all this other neat stuff that we can do here. Any questions on that? I'm going to go on to the next section. Okay, so your book then talks about adiabatic expansion of a gas. That's where they derive the P times V to the gamma power is equal to a constant. Again, that's a very nice little straightforward derivation. I highly recommend you do it. But what I'm going to do instead is I'm going to solve another problem with the stuff we've learned. This will be example 5. Uh, Actually, we only have 2 minutes to do that, so I don't think I'll be doing that. So what we have left here is something like example 1915 in the book, and then the examples on conduction. So still need to do, well, let me write this down in actual ink. Still need examples 1915. Let me see if there's any other major ones that I want to work on. Then we go into conduction. I'll tell you, conduction has Q over T and that's T in time, by the way, is equal to K. Oops, there I go again. K, which is a property of the material through which something's being heated, times A, the cross-sectional area. The larger the cross-sectional area, the more heat that can be distributed, times delta T, the temperature, over L, and this is called the temperature gradient. And this is conduction. So that's the only, well, that's one of the topics we're left to cover. Uh, there is a nice example in there, which is 1916. And then they talk about R, they talk about convection, and finally they talk about radiation, which gives us another law, and that law is Q over T is equal to epsilon, which is related to how well it absorbs or emits radiation, times the Stefan-Boltzmann constant, times the area times T to the fourth, and this is called the Stefan-Boltzmann law, where sigma is equal to 5.67 times 10 to the negative 8 watts per square meter Kelvin to the fourth. So there is an example in that one, and that's 17 and 18. I think that, oh, 17, 18, 19. So those are what we have left. I'm probably going to do those in a video over the weekend. And then, take questions if you have any next time and just start into the next chapter. But feel free to look at those or ask me questions, and I'll even try to let y'all know when I'm going on in case anybody wants to come during. But if I do actually make videos, that's what I'll do. So have a good one, Jen.
Okay. Thank you.
You're welcome. Don't forget you got a test this weekend.
Yeah, I know,
So,
I know, I know. It's been a crazy week. My kids were sick and now I'm sick. It's fun.
oh, I'm
Fun
sorry. It
stuff.
sucks. Well, well, I
It
hope you feel
rolls
better soon.
downhill sometimes. All right.
Yes,
Thank
it
you.
does.
You too.
Bye. Have a good
Bye.
one.
You too.
So I guess that's it. Didn't get nearly as far as I wanted to. Oh well.